continuing, I will call the Professor Felipe to introduce the Professor Swann Marx. Please, Professor Felipe.
Okay, thank you very much. It's my pleasure to introduce Professor Swann Marx. Swann is a senior researcher in Nantes, in France. He has been there since 2019. He has been a postdoctoral in Spain and in France. So he did his PhD in France under the supervision of Christophe Prieux and Vincent Adrieux. Okay, so it's a very well-known researcher in the area of analysis, control, and stability of partial and ordinary differential equations. So thank you very much, Swann. And he's been talking today about singular perturbation for a coupled KdV-ODE system. Okay? Thank you very much, Swann.
Well, thank you, Felipe, for the nice introduction. So, yeah, today I will talk about singular perturbation analysis for a coupled system composed by a Korteweg-de Vries equation, which is a PDE, with an ODE. So what I mean by singular perturbation analysis is that one of the two systems admits a different time scale, which means that one of the two systems is faster than the other one. And thanks to this assumption, I would say, hypothesis, then we can find results that are interesting. In fact, the singular perturbation consists in decoupling the system into two subsystems, I would say, that describes the fast system and the slow system. So this work is a joint work with Eduardo Serpa from the Universidad Católica de Chile. And so we will talk about this KdV-ODE system. So in many cases, you may face with a system with different time scales. For instance, if you look at electrical and a system which mixes electrical behavior and mechanical behavior, then you will have different time scales because the electrical system will be faster than the mechanical system. And when facing with this kind of system, we face also with a lot of difficulties. So, for instance, you may face with huge cost in numerical simulation. So you have to change the time steps to solve the system. So this can be difficult. So here we won't talk about the numerical aspects of these systems, but more about the asymptotic stability or the asymptotic behavior. But what we do in general when you look at this kind of system with different time scales is, as I said, we want to solve a limit system which describes approximately the behavior of the system when the fast system is sufficiently fast. So here is the system that we will look at. So we have a PDE which is given by the state y, and you have the coupling at the boundary, so which is represented by the state z, and you can see that z solves an ODE, and there is also a coupling in the ODE through the boundary conditions of the truss of the solution yxt0. Okay, so why we look at this kind of system? If you consider that yxt0 is something that you measure for the system, you can consider that you can control the system with this output, with this measurement. Okay, and so you want to stabilize the system with this output. Okay, but the problem here is that we consider that the control, in fact, the control has a dynamics which is given by a ODE. So here we look only at the linear KdV equations because, well, the nonlinear KdV equation is quite hard to handle. but this is one of our projects to look at this kind of system when the KdV equation is nonlinear. So here epsilon is supposed to be small, which means that the fast system in this coupled system is in fact the KdV equation. Okay. So we have several questions about this coupled system. So first, what are the conditions on A, B, and C such that the coupled system is stable? And if you suppose, epsilon sufficiently small, then do these conditions change? So can we weaken, in fact, the conditions that we have found before for every epsilon? And another questions that we won't discuss that much during this talk, but we will discuss it a little bit, is what is the behavior of the solutions with respect to small epsilon? Okay. So, okay, that is nice, but here we will first discuss a really simple example, which is a finite dimensional example, which is, well, this is quite simple because here we are facing with two ODEs and two scalar ODEs. So Y and Z belongs to R. Okay, so you have the same situation, in fact, and it's just that Y here is an ODE. So because of epsilon, the dynamics of Y is supposed to be faster than the one of Z, as I said before. And so in terms of asymptotic behavior, you want this system to be exponentially stable without the coupling, okay? Because you, in a sense, from an asymptotic point of view, you want to neglect the influence of this system with respect to the other one. And so we fix a negative. And this will be important in the following. So to treat this system in terms of asymptotic stability, you can use a lot of tools. Okay, but here we will focus on the Lyapunov method because this is the one that we will use for the KdV equation coupled with an ODE, and we will use what is called the forwarding approach, which is a Lyapunov-based method, and which is composed by two terms, this Lyapunov function. So the first one is for the fast system. So you know that for the fast system without coupling, you have a Lyapunov functional that exists. And the second term is the difference between Z and My, let us say, okay? And M has to be selected. So what is the idea here? The idea is to make converge Z to My, but you know that Y converges also to 0, so Z will also converge to 0. This is the point of the forwarding method. Just that you have to select a good M. And so if you take the time derivative of the system, you end up with the first terms that comes from the first term of the Lyapunov functional, so the two first term, and a second term here, the third term here, okay? And the idea of M is to select M such that the influence of Y disappears, okay? And so you take MA is equal to D, and you end up with this equality, okay? And then you use some Young's inequality, so alpha 1 and alpha 2 are the terms of the Young's inequality, and you end up with these inequalities, okay? So so you want this inequality to be less or equal than 0, okay? So that you can apply the Grenville lemma. Well, the first condition is quite simple. You have A, which is small, so you just have to, which is a negative, sorry. So you just have to choose alpha 1 and alpha 2 sufficiently small with respect to A. So this is not that difficult. And the second term is, in fact, a polynomial with an unknown, which is BD over A minus C. And so this is a polynomial of second order. So you can compute the square root of this polynomial and end up with this analysis, which says that B has to be sufficiently small, and BD over A minus C is between two positive constants, And then with these conditions, you have this system, which is this terms that is always negative. And so this Lyapunov function, this function is a Lyapunov function. Okay. So the question, as I said before, is okay. Now you have the analysis for all epsilon. What happens when epsilon is small, and when it is sufficiently small? And to do so, we will apply the singular perturbation principle, which is, as I said, consists in decoupling the coupled system into two approximated systems. So first, the reduced order system, which is the slower system, and the boundary layer system, which is the faster system. Okay, but how can one compute these two systems? Well, the idea is, in fact, to take epsilon is equal to 0. This is quite simple. So you suppose that epsilon is equal to 0, then you end up with y, which is equal to minus b over a times z, which is called the equilibrium point of the system. Okay, then we replace y, so this equilibrium point, in the second line of the dynamics, and you end up with this system, okay, which is called the reduced order system. And you can see, you can see that you have the constant c minus bd over a, which already appeared before when applying the forwarding method for the coupled system without any knowledge about the epsilon. Okay, this was just here. Okay, and here bd over a minus c was positive, so c minus bd over a is negative. So you can see that these conditions will appear, and a conditions for this system to be stable is that this term is negative. Then for the boundary layer system, you change the time scale, so you consider tau, which is equal to t over epsilon. You consider y bar, which is equal to y plus b over a z, which is in fact minus the equilibrium point that we have computed before. Then you take the time derivative with respect to tau, and you take epsilon equal to 0. So you end up with this system. Okay, and you know that this system is stable if a is negative. Okay, so as a recall, so we have the reduced order system, which is given by this first system in z bar, and the boundary layer system, which is just below. Okay, and the stability conditions, as I said, is a is negative and c minus bd over a is negative. So if epsilon is small enough, do these conditions all for the full system. This is the point of the singular perturbation method. And in fact, if you do the change of coordinate, which is just here, so y tilde, which is equal to y minus the equilibrium point, so b over a z, the full system can be written just like this. And so the constants, so the formula c minus bd over a appears here, and in the first system you can see that you have a y tilde and a term, okay, which is not that important, but this term is multiplied by epsilon. So you can, well, this is just an intuition, but you can guess that if epsilon is sufficiently small, then this term will not have any influence on the stability of this system. Okay, but if you use the same Lyapunov function on that before, okay, you can find an epsilon star such that if epsilon belongs to this interval, and for any a, b, c, d satisfying a negative and c minus bd over a negative, then there exists u1, u2 that is positive, such that you have this inequality. Okay, so this is quite nice. And in fact, the conditions are weaker than the conditions for all epsilon, because here c minus bd over a is not between two negative constant, and B, recall, was supposed to be sufficiently small. That was just here, okay? So the conditions are weaker. And in fact, this means that you just have to look at the two subsystems, so the reduced order system and the boundary layer system, and you can conclude that the full system is stable as soon as epsilon is sufficiently small. So for sure that this kind of result exists for general linear systems with matrices and everything. And there is a general result which says that for sufficiently small epsilon, the conditions for the reduced order system and the boundary layer systems to be stable, all for the full system, as I said, as soon as epsilon is sufficiently small. Okay, well, this result has been, for instance, is written in the book by Kokotovic, Khalil, and O'Reilly, that is from the 80s. And the strategy that is presented in this book relies on a frequency approach. So you look at so you transform the system with the Laplace transform and everything. Okay, but what about the infinite dimensional case? So can we hope having such a result for general infinite dimensional case? In fact, there are very few results, at least from my point of view, to the best of my knowledge, for the infinite dimensional setting. I just listed 2 papers, but maybe there are 2 more about this kind of results, but not that much, in fact. And this result, in fact, focuses only on a particular class of systems that are transport equations coupled with ODEs or a system of transport equations. And in fact, there is a very interesting result about this singular perturbation method for this kind of system, is that we have a counterexample of the result that has been found for the finite dimensional case, and it is just given by this example. Okay, so you have a fast ODE, okay, and a single transport equation, which is the slow equation. You can compute, as I did before, these 2 equations, the reduced order system and the boundary layer system. And you can see that the first system is, in fact, stable. In fact, it is finite time stable. You can prove it with the method of the characteristics. And the boundary layer system, this is quite obvious that this boundary layer systems is exponentially stable. So both systems are exponentially stable, but the full system is not. And you can prove it with the method of characteristics and by making a link between these kind of systems and difference equations. So you have for the difference equation, you have necessary and sufficient conditions, and you can prove that this system is not exponentially stable. Okay, so this is not a good news for us, but we will see that for the KdV equations, at least for the system that I presented, these singular perturbations works. So we go back to the KdV equation coupled with the ODE, and so you have the fast KdV equation and the slow ODE equation. And as I explained before, since the KdV equation is a fast system in this situation, so you want this system to be exponentially stable without the coupling, so without AZ, so by setting YXTL equal to 0. So the question is, okay, what are the stability conditions for the unique KdV equation without the coupling? So there are a lot of results about this kind of systems. In fact, if L doesn't belong to this critical length set, which is kind of horrible to read, but in fact it comes from the spectrum of the system, then the equilibrium point 0 is exponentially stable for the KdV equation. And in fact, if L belongs to this critical length set, we may lose the observability property of the output YXT0, so which means that this output may vanish. So this is not good for us, because then we won't have anymore the coupling between the KdV equation and the ODE equation, the ODE. So to understand this, so we take the energy. So this is the L2 norm of the equation square. You take the time derivative, and then you end up with this equality. Okay. If you take R is equal to 2 pi and you start from y0x, which is equal to y minus cos x, then you will have y0 dot 0 at 0 is equal to 0, which implies, in fact, that the energy will be always equal to y0, which means that you don't have the asymptotic stability. You have stability, but not the asymptotic stability. So the solutions won't converge to 0 as t goes to infinity. For the nonlinear KdV equation, which is interesting, is that you can prove the asymptotic stability, not the exponential stability of the origin, for some L that belongs to the critical length set. So just for your information. So this is a local asymptotic stability in the sense that the initial conditions has to be small. And we have a better result, in fact, that we have found recently, which is, well, not spectacular, but which is quite interesting. So this result was due to Ismaila Balogun and Daniela Astolfi and myself. Ismaila Balogun is a PhD student finishing, a PhD student finishing his PhD in one month. And in fact, we have proved that we are able to construct an ISS Lyapunov functional for the KdV equation. So because the stability, the exponential stability of the system was not proved. Yeah. So was not proved with a Lyapunov functional. Okay. So we've constructed an ISS Lyapunov functional. So what do we mean by ISS Lyapunov functional? This is a system which is ISS is a system with perturbation, so D1 and D2. Okay, sorry for the typo. This has to be D2 here. And in fact, it means that if D1 and D2 goes to 0, then the trajectories will go to 0. And if D1 and D2 are bounded, then the solutions will be also bound. So this is more or less what we mean by ISS Lyapunov, ISS stability. Okay, so in the following, we will follow the same procedure than for the finite dimensional system, and we will use the Lyapunov functional W given by the theorem which is just here. So what are the main results? So first, we have proved that for any epsilon, we can find, we know that there exists A star such that if A is sufficiently small and AC minus B is between two positive constants, then the origin of the system is globally exponentially stable. So you can see that this is quite the same condition than for the finite dimensional system. So the example was not that bad. And this result, in fact, can be seen as a generalization of the result of the papers that I have cited before, where we have considered the case where B is equal to 0 and C is equal to 1. And we have also a result which is maybe more interesting, which says that for any A, B, C such that B minus AC is negative, then there exists an epsilon star such that if epsilon belongs to this interval, then the origin is globally exponentially stable, which means that the singular perturbation method applies for the coupled KdV-ODE system. So to compute the radius of a system, we suppose that epsilon is equal to 0. So you end up with this boundary value problem. Okay. So I call it a boundary value problem because, okay, T doesn't have any influence of the solution of this system, which is just a parameter. You can find an explicit solution to this problem, which is given by this function. So Z, which comes from the boundary conditions, and F, which is this function. Okay. We can find Hx T0, which is equal to minus AZ, and we replace it in the ODE, and so you end up with Z bar dot, which is equal to B minus AC Z bar. And so you know that if B minus AC is negative, then the system is exponentially stable. So this is the condition that we have seen before in the theorem. Then, for the boundary layer system, we do exactly the same computation than before, and you end up with this system. Okay, so just the KdV equation without any coupling. And you know that if L doesn't belong to the critical length set, then the system is exponentially stable. So the only conditions after applying the singular perturbation method is to ask BAC to satisfy this inequality. Okay. So as in the finite dimensional case, we will follow a forwarding approach, which is in fact consists in introducing this kind of Lyapunov functional. So here, this is the Lyapunov functional for the KdV equation. So without the coupling that we have constructed before in the paper that I have cited before, and a term which is, I would say, the forwarding term. But here, so before M was a scalar, but here this is an integral operator, so with the kernel, and this kernel is the solution of this boundary value problem, for which we know that there exists a solution. Okay, so this is a little bit more difficult than in the finite dimensional case, but this is the same problem, I would say. So first, we use the ISS Lyapunov functional. So we consider AZ as a perturbation. Okay, so you end up with this term. Okay, this inequality. Then you integrate by part. You use the form of M, and you use some Young's inequality with alpha as the term of the Young's inequality, and then you end up with this inequality. Okay. And at the end, the Lyapunov functional is just satisfied, so the time derivative of the Lyapunov functional satisfies this kind of inequality. Okay, this kind of inequality already appeared in the finite dimensional case, so we know how to treat this. So you take alpha sufficiently small and A sufficiently small and the AC minus B between two positive terms, and then you end up with this polynomial, which is always negative. Okay, so this is how we prove the asymptotic stability of the system for this kind of system for every epsilon. Sorry. Then for small epsilon, you consider y tilde, which is equal to ytx minus the equilibrium point, and you end up with this coupled system. Okay. And you can see that there you have the KdV equation, okay, with a term which is multiplied by epsilon. So you can guess again that if epsilon is sufficiently small, then you will only have this equation, okay, with just the KdV equation. And if you use the same Lyapunov functional than before, then you obtain the same result. But we skip the computations because this is maybe too heavy for us. Okay, and we have also another result, which is in fact which is the following one. Okay, if we consider the initial conditions that depends on epsilon, okay, in this way, then you can have the behavior of the trajectory with respect to epsilon just like this. Okay, and the idea is to use again the same Lyapunov function. So okay, so we have done this analysis in the case where we have a fast KdV equation and a slow ODE. But does this singular perturbation method apply for the case where the ODE is fast? And the answer is yes, but some adjustments needs to be done. So we compute the reduced order system, okay? So we do exactly the same thing. And we compute the boundary layer system, okay? So So here the equilibrium point is just given by this term, and you have a KdV equation which is maybe more difficult to analyze, but we have some non-results about this KdV equation. You know that this KdV equation is exponentially stable as soon as AC over B is less than 1, strictly. Okay, and for the boundary layer system, well, you have B that has to be negative. And we call that we have this Lyapunov, this ISS-Lyapunov functional. Hall theorem says that, okay, as soon as A squared, C squared, B squared is less than kappa 3, kappa 2, so that comes from the this ISS-Lyapunov functional, we know that there exists epsilon star such that for any epsilon in this interval, then the origin is exponentially stable. That's nice. But for initial conditions that are not anymore in L2, but in H3 with this kind of compatibility condition. And the question is, okay, why we need these initial conditions to be so regular? In fact, when you do the change of coordinates, so you consider Z star, which is equal to Z minus the equilibrium point, so which is here y minus C over B yx t0. In fact, you want to differentiate this Z tilde with respect to the time, and which requires, in fact, a higher regularity of the system. So you cannot apply the method that I have applied before for this kind of system, except if you take the higher regularity. So what we have done here is, okay, we have applied the singular perturbation analysis for a coupled KdV-ODE system, and to do so we have applied a method that it was not that common to use the forwarding method for the singular perturbation, even in the ODE case, but we have done it for this kind of system. And we have several open problems. So what about the case of coupled PDs? So two PDs that are coupled. In fact, we have done something recently with Eduardo Serpa and a PhD student, Gonzalo Arias. So about the coupling of a heat equation and a wave equation. And this model, in fact, is is inspired by an earthquake phenomenon. And what about the case of operators generating semigroups? So the general case with operators, is it possible to find a general result? And well, in fact, this is maybe difficult, but we in fact really want to understand why the counterexamples doesn't work. And we are currently working on this kind of questions. And well, that's it from me. And if you have any questions, don't hesitate to ask.
Okay, thank you very much, Swann. Thank you very much. Very nice talk.
Thank you.
I will open the mic for anyone who wants to ask something, to make some comment. Any comment, question? Alguma pergunta, pessoal? Alguma pergunta? Podéis usar el chat también. So you can use the chat to talk, to ask something. I can read. So I have a small question, but it says, for instance, if you try to consider KdV, linear KdV plus coupled with the transport equation, did you guys think about that? Like, because you asked about PD, coupled PDs, but maybe if you already tried something, some special cases, like
No, we didn't look at this kind of problem, but that can be interesting. Well, I think that you will we will find the same counterexample than before, just that the proof will be difficult. In fact, we have a guess about this counterexample. We think that the two systems, the two uncoupled systems, so without the coupling, have to be asymptotically stable. And so maybe the case that you mentioned is a case that where we will have this kind of issue, in fact.
I see. And to pass to the nonlinear case, the nonlinear KdV with ODE, in fact, what would be the main difficulty? Like, because you get something quite explicit here, like you use Lyapunov, but what would be the main drawback to?
First, the main difficulty is to understand how to prove the asymptotic stability with the method that are used in general. But I suppose that this is the main difficulty, because well, first, the method that I have presented cannot be applied. That's for sure, because for the nonlinear KdV equation, since you have a polynomial stability, so it is kind of difficult to construct the Lyapunov functional. So we have to look up at the solution itself, and maybe so we have. I don't have any clue about this kind of result, but sure, we want to do this.
I see. Okay, thank you very much. Does anybody have any question, comment? Okay, so I think let me check the chat. No. Okay, Swann, thank you very much. And really nice talk. I really enjoyed it. Juan,
thank you very much.
Juan, pode terminar o vídeo se quiser. Swann, okay, so